Hello guys, we'll be continuing with molecular biochemistry. Now we'll be discussing about histones mainly and basically the histone modifications, right? Mainly in this we have histone acetylation and histone deacetylation. We'll be discussing further briefly into this. First we need to know again what are the histones, right? The features to remember. Histones are the basic proteins. The base is mainly present. The amino acids which are basically present, which are the basic amino acids which are basically present, are lysine and arginine. Furthermore, it has 8 subunits, which are H2A, H2B, H3, H4, and all of them are present twice, so that makes it 8 subunits with an external subunit that is H1. H1 is very important because it's the largest external subunit. It is more basic and it has a role in basically keeping together the nucleosome core together. It keeps it together, right? Like we discussed the structure previously, there's this 8 subunit structure for histone with the 2 loops of DNA. This makes up the nucleosome basically, and what's keeping it together is this external structure of histone that is H1, right? So this is very important, right? Right, this is mainly about histones that we discussed. Now moving on to the acetylation. Acetylation, basically by its name we say it's addition of an acetyl group or acetyl CoA. Now what happened is that this is the histone protein, right? Histone protein has a positive charge, and what has a positive charge? The basic amino acid, that is lysine. To remember the amino acid lysine, okay, this has a positive charge. This lysine undergoes acetylation mainly. The lysine residues of histones undergo acetylation via the HAT enzymes, HATs, which is histone acetyl transferases. The acetyl CoA group is added to this lysine, and what may basically happen is that this acetyl CoA group has a negative charge. Now lysine is already attached to DNA, right? DNA looping, twice looping we see in a nucleosome. Lysine with its positive charge has been attached to DNA with its negative charge. There's electrostatic attraction going on that's keeping them together. Now what happens here is that there is an acetyl group coming here with a negative charge. This negative charge and positive charge results in neutralization. It basically, we say that acetyl group is neutralizing lysine here, and it's weakening the bond between DNA. So what happened is that now we have more relaxed DNA or chromatin, and as you remember, this is euchromatin. So we basically have conversion from heterochromatin to euchromatin. So what we discussed here already, that histones are keeping the nucleosome cores together, DNA more compact and condensed. So histones with DNA loops are very compact and condensed into heterochromatin structure, and when needed it has to undergo histone acetylation, which we discussed here, to make a part of it more relaxed, right, so that it can undergo transcription. So mainly the point here, that the summary of this point says that histone acetylation is directly proportional to more transcription, you can say, or you can say it activates transcription of DNA, right, when needed. Why I'm saying when needed? Because it's a reversible process, okay, reversible process, and when needed not to, it can undergo deacetylation, means a removal of that same acetyl group via the deacetylase to make the DNA back more condensed, okay, or to turn the euchromatin back to heterochromatin. Right, simply as that. This is like more of a detail of the process of what is going on. Histone acetylation. Histone has a lysine residue with a positive charge, and acetyl group comes while the acetyl transferase, it attaches to lysine to basically neutralize its charge, and that charge was a main thing to basically attract DNA and keep it together. Now this charge is neutralized and DNA is now free, more relaxed, and as it is relaxed, it is more prone to definitely transcription. Now more transcription will occur, and whatever it is needed for, and it's a very regulated and balanced process between acetylation and deacetylation. Not that the DNA is more free, or not that the DNA is always condensed. When needed, it has been transcripted. When not needed, it's deacetylated, and it is protected this way. And why this balance is very important is because there's certain diseases in which this balance is disturbed, and we get to see the autoimmunity, we get to see different disorders going on there. I'm going to discuss a few of them, basically two of them. Now there's this example of disease that we see, in which we see like increased histone acetylation is drug-induced lupus. Now the two mechanisms basically going on, if we go into the detail, there is acetylation going off or going on the drug itself, the drug that is causing it, and furthermore there is basically that, and then there is also increased basically histone acetylation of the enzymes, right? Basically not the enzymes, I meant to say, like, there is inhibition of the deacetylases, so there will be more acetylation. So if I write it down, I would say there is inhibition of deacetylases, which is responsible for deacetylation when needed, and that will be inhibited, so there will be more acetylation, histone acetylation. And secondly, there is acetylation of drug. Now, slow acetylation, I must say slow. This is a very important word here, because acetylation of the drug is needed in lupus. In a condition, wherever it is, in whatever condition it is prescribed for, to basically excrete it in certain conditions where acetylation is important for the drug to basically cause its excretion, to basically remove it from the body. Now there's certain genetic variations in certain bodies or in certain humans that cause its toxicity to become prominent because of the slow acetylation. So we call those people as slow acetylators. In these certain people, what happens is that this drug is not like acetylated in the wild that it is to be acetylated. And what happens is that due to the slow timing, the drug comes up with its side or adverse effects, and basically causes this lupus. The examples we see in these kind of drugs is isoniazid, mainly it happens with that, and procainamide. And in the other case we see valproic acid. So a few of the examples to remember, okay, in these cases. Right, this was one of the examples for acetylation. What happened is that in drug induced, it's not related to it's not related to SLE itself, because there is anti double helix DNA antibodies in SLE itself. In this we have anti-histone antibodies, okay, working on. That's why it's important to alter with the with deacetylases, inhibition of deacetylases, and or slow acetylation of the drug, whatever the complicated mechanism. But need to remember there's anti-histone antibodies. Histones are basically involved in this drug-induced lupus to be the culprit in causing the effects. So this is kind of a example for this, that there is increased acetylation going on, and there are slow acetylators that are causing these two kind of effects in drug-induced lupus. Another example for deacetylation to remember is Huntington's disease. In Huntington's disease, again, the balance between this acetylation and deacetylation is disturbed. What happened is that there is a gene mutation, right? Huntington's genes is mutated. Due to genetics or whatever. And what happened is that there is a formation of this Huntington's protein, specific mutated protein. Now this protein comes up, and this protein is the culprit, right? It basically forms a specific binding protein. It basically, how it forms that, it comes and it's coester or collects all the histone acetylases that we discussed in the process to form the CBP, which is the binding protein, right? And this is going to bind, and this is basically going to, this binding protein is going to bind to the protein to ultimately result in preventing the histone acetylation, right? And gene silencing. So there is increase in decrease in histone acetylation. Not that we're not discussing deacetylation increase, but decrease in histone acetylation and more gene silencing, right? So there is no more transcription, there is genes more compact now, not available for being transcribed, and so with others, right? So again, the mechanism is all very clear, but to just remember that there is decreased histone acetylation going on in Huntington's disease that results in more gene silencing ultimately. So this is one of the examples to remember, as diseases, how it is related to histone modifications, and how important this balance is between histone acetylation and deacetylation that results in this balance that results in controlled transcription of the DNA. So this is it for the video today. We'll continue further with the other topics.